Hello again and welcome to week 7. This week we delve into a fascinating and powerful topic, eigenvalues and eigenvectors. These concepts might seem abstract initially, but they provide deep insights into the behavior of matrices and linear transformation. They essentially help us find the fundamental directions or axes along which a transformation acts simply by stretching or shrinking. We'll explore their definition, build intuition, see how to calculate them using NumPy library, and discuss their important application, particularly in machine learning with techniques like PCA. But before we start, I'd like to mention and remind that it's a friendly and inclusive space. And so this session will be recorded. Okay, here's our updated plan for today, broken down into more steps. We'll start with some motivation. Why are these concepts worth studying? Then we will introduce the core mathematical relationship, the definition equation. We will clearly define the terms eigenvectors and eigenvalue based on that equation. We will spend time on the geometric intuition. What do they look like? Mentioning the 3 blue, 1 brown resource. We also will briefly cover the theoretical method for finding them using the characteristic equation involving the determinant. Next, we will introduce a practical tool, NumPy's IG function from the linalg module. We will then work throughout several NumPy examples, a basic 2x2 case with verification and 3x3 example, an insightful case with a diagonal matrix and an example showing complex results. We will give a brief overview of where eigenvalues and eigenvectors are used. We will then focus specifically on PCA, principal component analysis, explaining how it relies on these concepts. And finally, we will summarize the key ideas. Before diving into definitions, why should we spend time on eigenvalues and eigenvectors? Because they help us understand the core behavior of a linear transformation represented by a square matrix A. Instead of seeing the transformation as a complex mix of rotations, shears, and stretches, acting on the whole space, eigenvalues and eigenvectors allow us to identify spatial fundamental directions. These directions often represent axes of maximum stretch or compression, directions of stability in dynamical systems, or principal model of vibration in physics and engineering. By understanding these fundamental directions and how the transformation acts along them, the scaling factor given by the eigenvalues, we can often simplify the analysis of complex systems. A prime example we will see later is dimensional reduction in machine learning using PCA. These concepts are truly foundational and appear across many scientific and technical fields. The entire concept of eigenvalues and eigenvectors revolves around this single elegant equation shown on the slide. Let's break it down. So we start with a square matrix A. Remember, this represents our linear transformation. We are looking for two things: a non-zero vector, which we call v, a scalar, a single number, which we call lambda. These three components, a, v, lambda, are related by the equation a times v equals lambda times v. This equation captures the core idea. Applying the transformation A to the vector V yields the exact same results as simply scaling the original vector V by the factor lambda. This equality is the mathematical heart of eigenvalues and eigenvectors. So, based on the defining equation, A times V equals lambda times V, let's clearly state the definitions. As eigenvector, represented by V, is any non-zero vector with a very specific property. When you apply the matrix transformation A to it, the resulting vector A, V, points in the exact same direction, or precisely the opposite direction, as the original vector V. It stays on the same line passing throughout the origin. It doesn't get rotated off that line. Remember, V cannot be zero vector. An eigenvalue represented by lambda is the specific scalar number associated with a given eigenvector. It tells us precisely how much that eigenvector V was scaled along its line during the transformation. If lambda is 3, the vector tripled in length. If lambda is 0.5, it halved. If lambda is minus 2, it flipped direction and doubled in length. Every eigenvector has a corresponding eigenvalue that describes the scaling factor along its direction. Let's visualize this. Imagine the grid lines of your coordinate system. Applying a matrix transformation A might stretch, shear, or rotate that grid. Most vectors drawn on that grid will point in completely new directions after the transformation. However, the eigenvectors represent those special directions that, after the transformation, still lie perfectly along the original direction lines. So the lines themselves might have stretched or shrunk. Think of them as invariant directions. If you draw a vector along an eigenvector direction, applying A just scales it. It doesn't rotate it off that original line. The eigenvalues tell you the scaling factor along each of these spatial eigenvector directions. Maybe space gets stretched by a factor of 3 along one eigenvector direction when lambda equals 3, and shrunk by a factor of 0.5 along another lambda 0.5. So, eigenvectors and eigenvalues essentially reveal the underlying axis of the transformation's action. The directions along which the transformation acts purely as a stretch or squish, potentially with a flip if lambda is negative. Again, for a fantastic visual explanation, I highly recommend the 3 blue 1 brown video of this topic. It makes this abstract idea much more concrete. I'll share a link It's Discord channel also. How do we find these eigenvalues and eigenvectors mathematically? While we'll use NumPy for calculation, understanding the theory is useful. We start from the definition. A times V equals lambda times V. As we saw briefly before, we can rearrange this by introducing the identity matrix I, where I times V minus lambda I V equals 0. Factoring out V gives I minus lambda times I times V equals the 0 vector. Now we are looking for solutions where V is not the 0 vector. For the equation, some matrix times V equals 0. To have non-zero solution for V, the matrix itself, here A minus lambda I, must be singular. And what's the condition for a matrix to be singular? Its determinant must be 0. This gives us the characteristic equation. Determinant of A minus lambda I equals 0. This equation involves the unknown eigenvalues lambda. Solving this equation, which usually turns into finding the roots of a polynomial, gives us the possible values for the eigenvalues lambda. Once you have found an eigenvalue lambda, you plug the specific numerical value back into the equation A minus lambda I V equals 0 and solve the system of linear equation for the vector V. The non-zero solution V are the eigenvectors corresponding to that eigenvalue lambda. This process can be done by hand for small matrices, and Khan Academy provides good examples if you want to practice that. But for larger matrices, we turn to computational tools. I'll share a link to Khan Academy part Discord channel also. Fortunately, we don't need to solve the characteristic equation manually in practice. NumPy's linear algebra module, linalg, provides a very convenient function, ig. The function call is typically np.linalg.ig, for example, of A, where A is the square matrix you want to analyze. This single function does all the hard work for us and returns two pieces of information: an array containing the calculated eigenvalues, the lambda values, a matrix where each column represents the eigenvector corresponding to the eigenvalue at the same position in the first array. It's crucial to remember that the eigenvectors are arranged as columns in this output matrix. So let's see np.linalg.ig in action with our first example. We will use a simple 2 by 2 matrix A, where the first row contains the element 4, 2, and the second row contains the element 1, 3. So let's explore this code execution. We define A as a NumPy array. Then we call eigenvalues, eigenvectors, and equal np dot linalg dot ig with passing a. The code prints the results. NumPy found two eigenvalues, 5 and 2. It also gives us a matrix containing the corresponding eigenvectors as columns. The first column is the eigenvector for lambda 5, and the second column is the eigenvector for lambda 2. Now let's verify the fundamental relationship. AV equals lambda V. For the first pair, we take the first eigenvalue. Lambda first equals 5. We take the first eigenvector V1, which is the first column of the eigenvectors matrix. We calculate A at V first, using the at symbol for matrix multiplication. We also calculate lambda first with V1 scalar multiplication. And if you run this code, you see the result. The printed result for A at V first and lambda first multiply V first should be identical or very close due to computer arithmetic. We use np.allClose to confirm they are numerically very close. The output, as you can see, true, which confirms our results satisfy the definition. The np.linalc.ig function works just as well for larger square matrices. And for example, let's try a 3 by 3 example. We define matrix B as shown. And let's explore quickly this code execution. Again, as you can see, we simply call eigenvalues underscore B, eigenvectors underscore B equal np linalc.ig, and we pass B. NumPy calculates the three eigenvalues for this 3 by 3 matrix, which turn out to be 3, 1, and 0, and provides the corresponding eigenvectors as the columns of the eigenvectors underscore B matrix. Just to show it works consistently, the code includes an optional verification step. This times for the second eigenvalue, where lambda equal 1, and its corresponding eigenvector, the second column. We calculate B at V second and lambda 2 multiply V second. Let's look at a specific insightful case, a diagonal matrix. A diagonal matrix, like in our example D, has non-zero values only on its main diagonal and zeros everywhere else. What happens when we find its eigenvalues and eigenvectors? So let's explore quickly this code execution. We define the diagonal matrix D. We call our np.linalc.ig and pass D. Now observe the results carefully. The calculated eigenvalues are 5 minus 2 and 3. Notice that these are exactly the numbers on the main diagonal of our matrix D. This is a general property for a diagonal matrix or a triangular matrix. The eigenvalues are simply the entries on the main diagonal. Now look at the eigenvectors matrix. allowing for potential floating point variation or single flips. Eigenvectors are unique only up to a scalar multiple. The columns are essentially the standard basis vectors. As you can see, 1, 0, 0, second row 0, 1, 0, and last 0, 0, 1. Throughout NumPy might output 0, minus 1, 0 for the middle one, which is just minus 1 times at row 0, 1, 0. This also makes sense. A diagonal matrix just scales the standard coordinate axis, so the standard basis vectors are indeed the eigenvectors. This example gives a nice concrete connection between a matrix structure and its eigenvalues vectors. These are the standard basis vectors, and let's visualize why this makes sense on the next slide. So, let's visualize the action of a diagonal matrix. Since plotting in 3D is more complex, we will illustrate the concept using a 2D diagonal matrix. Say D in our example is a 2 by 2 matrix where the first row contains the element 5, 0, and the second row contains the element 0, minus 2. We know its eigenvalues are 5 and minus 2. And the eigenvectors should be the standard basis vectors 1, 0, and 0, 1. Let's take a look at code. We define this 2D diagonal matrix at D underscore 2D. We take the standard basis vectors V1 underscore yesterday equals 1, 0, and V2 underscore yesterday equals 0, 1, which we expect to be eigenvectors, and another vector V underscore other, which equals 1, 1. We transform them by multiplying with our D underscore to D. The code then plots the original vectors. In blue, where first underscore std, where 2 underscore std, and green, where underscore where other. And their transformed version, red at the first, the second, and orange at the underscore other. So if we run all this code, we'll see this beautiful plot. So let's look at the plot. The first basis vector, the first underscore std, which equals 1, 0, blue arrow along the positive x axis, is transformed into the v first, which equals 5, 0, is red arrow along the positive x axis. It stayed perfectly on the x-axis. Its direction or span is unchanged and was scaled by a factor of 5. Its eigenvalue. The second basis vector, v2 underscore std, with parameter 0, 1, is blue arrow along the positive y-axis. It transformed into the v2, which equals 0, minus 2. It's our red arrow along the negative y-axis. Again, it stayed perfectly on the y-axis. Its direction span is unchanged, but it was scaled by -2. Its eigenvalue, meaning it flipped direction and stretched to length 2. The other vector, which is v underscore other and equal 1, 1, as you can see, it's green uh, arrow, gets transformed to dv underscore others, which equals 5 minus 2. And you can see it's orange arrow, which is clearly pointing in a different directions. This confirms visually that for a diagonal matrix, the standard basis vectors are the eigenvectors, and the diagonal entries are the corresponding eigenvalues, representing the scaling along each axis. Finally, let's revisit the case where eigenvalues might not be real numbers. Consider matrix R, which is 2 by 2 matrix where the first row contains the element 0 and -1, and the second row contains the element 1 and 0. Which geometrically represent a 90-degree counterclockwise rotation. So let's quickly explore code execution. What you can see, we define R and call our function and p dot linalc dot ig and pass our matrix R. Looking at the output, NumPy returns eigenvalues and eigenvectors that contain the letter J. As mentioned before, J represents the imaginary unit in Python. This means the eigenvalues and eigenvectors are complex numbers. Why? So because a pure 90-degree rotation into the doesn't leave any non-zero vector pointing in its original direction or the exact opposite. There are no real eigenvectors. However, the concept extends to complex numbers, and NumPy correctly finds the complex eigenvalues and eigenvectors that satisfy a times v equal lambda times v in the complex space. This is common for matrices representing rotation. Let's dive a bit deeper into one key application, PCA, or principal component analysis. Imagine you have a data set with many features, maybe dozens or hundreds of measurements for each data point. Working with such high-dimensional data can be difficult. So our PCA, principal component analysis, is a technique designed to reduce the number of dimensions or features. The goal is to simplify the data by projecting it onto a lower dimensional space, but to do so intelligently, preserving as much of the original data's variation or spread as possible. Why would we want to do this? Reducing dimensions can make data much easier to visualize. We can often reduce complex data down to 2 or 3 dimensions to create scatter plots. It can significantly reduce the computation resources needed to train machine learning models. It can sometimes help reduce noise by focusing on the directions with the most significant signal variance. And it helps combat the curse of dimensionality, a set of problems that arise when working with data in very high dimensional spaces. So, how does PCA actually work? And where do our eigenvalues and eigenvectors fit in? The process generally involves these steps. First, you typically standardize your data. Then you calculate the covariance matrix of your data. This square matrix captures how each feature in your dataset varies with every other feature. If two features increase together, their covariance is positive. If one increases while the other decreases, it's negative. If they are independent, it's near zero. Next, you find the eigenvalues lambda and eigenvectors v of this covariance matrix. Since the covariance matrix is square and symmetric, this will be real numbers. And now comes the crucial interpretation. The eigenvectors of the covariance matrix represent the principal components of the data. These are new orthogonal perpendicular axes that point in the directions where the data spreads out the most. The first eigenvector points in the direction of maximum variance. The second, orthogonal to the first, points in the direction of the next highest variance, and so on. The eigenvalue corresponding to each eigenvector tells you exactly how much variance exists in the data along the specific principal components, eigenvector direction. And finally, to reduce dimensionality, you look at the eigenvalues and rank them from largest to smallest. The largest eigenvalues correspond to the principal components that capture the most information, variance. You decide how many dimensions you want to keep, say k dimensions, and select the k eigenvectors associated with the k largest eigenvalues. You then transform your original data by projecting it onto this smaller set of k eigenvectors, effectively creating a new data set with only k dimensions that still captures the most significant variance patterns of the original data. Let's quickly recap the main points from today. We defined eigenvectors v as non-zero vectors whose directions is unchanged by matrix A, and eigenvalues lambda as the scalar factors by which they are scaled, related by A times v equals lambda times v. Geometrically, eigenvectors represent the invariant axis of transformation, and eigenvalues represent the scaling factors along those axes. While theoretically found using the characteristic equation, determinant of A minus lambda I equals 0, we practically calculate them using numpy's function np dot lin alg dot ig, and we pass here our matrix we want to calculate. NumPy's ig function returns an array of eigenvalues and a matrix whose columns are the corresponding eigenvectors. We saw it works for various matrices, including diagonals ones, where eigenvalues are the diagonal entries and can produce complex results, for example, for rotation. A key application is principal component analysis, PCA, which uses the eigenvalues and eigenvectors of the data's covariance matrix to identify principal components, directions of maximum variance, and reduce dimensionality effectively. So, for your homework for next week, I encourage you to first take some time to review the concepts we discussed today. Second, I'll share with you necessary to studying part from Khan Academy and three blue, one brown. Also, I prepared at Kaggle notebook and placed here all Python code which I used in today's session and in previous two. And I'll share all these links in Discord channel and a description under recorded today's session on our YouTube channel. So, this brings us to the end of today's session. Thank you all for your participation. It was great to have you all here. If you have any questions at all, don't hesitate to reach out on our community Discord channel. This session was recorded and will be available on our GDG Ahlen YouTube channel later. So if you want to review it, feel free. I really appreciate if you could take a few minutes to fill out the post-event feedback form. Your feedback is invaluable in helping us improve and make future sessions even better. Once again, thank you all for joining. See you in our next session next Sunday. Until then, keep learning, experimenting, and building with AI.